アミノ酸神経伝達物質のになるということで。こけないようにするには脳細胞大事です。
So, user Y receives C2. What do they know? What does user Y know when they receive C2? They know C2. They received it. Do they know anything else? If so, what? They know the public key of C2 is the ciphertext. We have X and Y and Z as the users in these examples, so they know the public key of. Okay, we assume that we always know the public key of other people. By definition, Y knows the public key of X because it's public. What else do they know? Or what do they not know, and why don't they know it? Do they know P2? Does Y know P2? Someone's nodding their head. Anyone will have a vote. Hands up for yes. Does Y know P2? If you don't put your hands up, then you will get an extra question in the quiz. And I recognise your faces, so remember your names, don't worry. Alright, two options, yes or no. Does Y know P2? Hands up for yes. Does Y not know P2? Alright, we have a few people voting, good. Why does Y not know P2? What's your opinion? Why do they not know it? They know C2, what about P2? Anyone can help? You voted no. Why do they not know P2? It was sent from X, yes. And it was encrypted by X. Can they decrypt it? Can Y decrypt C2? If they can decrypt it, then they'll find P2, correct? But you said they can't find P2. Now you've explained to me that they can. The question is, can Y decrypt C2? Well, with public key encryption, if C2 is obtained by encrypting using the public key of the user, then it can only be decrypted using the corresponding private key of that same user. C2 is obtained by encrypting using the public key of X. The only way to decrypt that is using the private key of X. PRX, we would know that. And the private key of X is known by who? Private key of X is known by X. Private means secret just to X. So Y does not know the private key of X. When Y receives C2, they cannot decrypt, because they don't have the private key of X. So in this case, Y does not know P2. Some people voted for that, but didn't have the right reasoning for that. It's because to discover P2, you need to have the private key of X, and only X has that. So remember, with public key encryption, if it's encrypted with one key in a pair, say the public key, it can only be decrypted with the other key in the key pair, the private key of the same user. What if X receives C2? Do they know P2? X receives this. Do they know P2?
Yes.
Why?
Because
X has the private key of X, and P2 is encrypted with the public key of X. Whoever has the private key of X can decrypt. X has the private key of X, so they can decrypt and learn P2 in this case. Okay, so X knows P2. Y, if they receive, would not know P2. So this provides confidentiality. The way to achieve confidentiality with public key encryption, if you want to send a secret message to someone, you encrypt using their public key. Let's say Z send this message to X. Z encrypts the message using the public key of X, such that only X can decrypt, because only X has the private key. So that's the role of public key encryption for confidentiality. It works in most algorithms. It works the same if we use the keys in the opposite direction. If you encrypt with the private key of X, you can only decrypt with the public key of X. So what happens here? Someone encrypted P3 using the private key of X, and they obtained C3. What if Y receives C3? What does Y know? Do they know P3? This is logic. There's not much detail the algorithm will go through. It's just some logic if you remember the rules. Why? You're saying no? Why can't they know P3? What do they need to know P3? P3 was encrypted with the private key of X. To decrypt it, to decrypt the ciphertext, what do you need? You need the public key of X. Remember, the keys are in pairs. If you encrypt with one, you can only decrypt with the other. It was encrypted with the private key of X, so if you have the public key of X, you can decrypt. Who has the public key of X? Everyone. It's public. So Y receives C3, they can decrypt, and they can learn P3 in this case. So yes, they do know P3. There's no confidentiality here. The message is public. We can see what it is. What else do we know? If it successfully decrypts with PUX, what does Y know? And this is an important role of this public key encryption. What does Y know when it decrypts? They know the plain text and who sent it? Who created it? It must must have been created by X. Because if P3 was encrypted with the private key of X, and then we can successfully decrypt the ciphertext with the public key of X, then that implies that the only person who could have created that message is X, because the only person in the world that has the private key of X is X. So this is performing some form of authentication. Y receives C3, they decrypt with the public key of X, they learn P3, but they also learn this message, P3, definitely came from X. No one else could have sent this message because no one else could have encrypted with the private key of X. So that's the role of public key encryption for authentication. Just going back, you see we're using the keys in the opposite order. For confidentiality, encrypt with the destination's public key. For authentication, encrypt with the source's private key. X encrypts the message with their private key, they send it to someone, that person who receives can verify it came from X by decrypting with the public key of X. So we've got two roles of public and... Have I missed one? Maybe I have. Right, there's another one. Y receives C3. What if Z receives C3? Maybe Z's malicious. What can they do? So same equation. Does Z know P3? Yes, they do, because you need the public key of X to know P3, and it's public. So yes, Z knows C3. Can Z verify it came from X? Yes, because if it does decrypt with the public key of X, that means it was encrypted with the private key of X, so Z also knows it came from X. From Y and Z's perspective, they know the same. So everyone can verify this message, everyone can see the contents. We can combine the two forms of public key encryption to provide both confidentiality and this authentication. That is, starting on the inner part, take our message, our plaintext message, P4, encrypt it with a private key of X, so let's say user X does this. Then the output of that, encrypt all of that with the public key of Y, and we get some ciphertext C4 and send it to Y. Y receives C4. What do they know? So you could work from the outside first, from Y's perspective. To decrypt this, Y needs the private key of Y. Y has that, so they can decrypt the outer layer. Then they can decrypt the inner layer because they need the public key of X to decrypt the inner part, and the public key is known by Y. So they decrypt the inner part, they learn P4, so they find out what is the plaintext, and they know it came from X because it was encrypted with the private key of X. So this is a way such that Y receives the plaintext, and they know for sure this message came from X. What if an attacker tries to do that? They receive the message, Z for example. Can they see the plaintext? Can Z see the plaintext P4? Why not? Z needs the private key of Y to decrypt the outer part. The outer part is encrypted with the public key of Y. Z therefore needs the private key of Y to decrypt, and Z doesn't have the private key of Y because it's private just to Y. So Z cannot decrypt the outer part and therefore cannot see the inner part and cannot see the plaintext. So we have confidentiality. Other users cannot see the plaintext. Then we have authentication. The user that gets the plaintext can verify who sent it. So we can combine the two modes. Remember how public key encryption is used. And it's quite simple. Encrypt with one key, you can only decrypt with the other key in the pair, because we have key pairs. And in both directions. If you encrypt with the public key, you can only decrypt with the private key. And if you encrypt with the private key, you can only decrypt with the public key of the same key pair. And to provide confidentiality, encrypt with the destination's public key. To provide authentication, encrypt with your private key. And this becomes very useful in many applications today, public key encryption, especially for signatures. You don't have those slides, but the idea was just to think about and to remember those rules and then apply them to solve some problems. Any questions before we return to the slides? Public key encryption, we had a pair of keys, and it's shown here that the rules for confidentiality encrypt with the public key of the destination. For authentication, encrypt with the private key of the source. That's what we just did, that's all. Only the person, for confidentiality, only the person who has the private key can decrypt. And for authentication, we can verify who sent the message using their public key. So if it decrypts with PUA, it means it must have been encrypted with PRA, it means it must have been sent by A. That's how we apply authentication. And that's about all we want to know about public key cryptography. So a few more slides. Where is it applied? So where is it useful? Well, we can encrypt messages, but for confidentiality we can have secret messages using public key encryption, but in practice it turns out the public key encryption algorithms are generally much slower than the symmetric key encryption algorithms. So if you want to encrypt a large message, you would use a symmetric key encryption algorithm, because public key encryption is generally very slow, or much slower. So they both can provide confidentiality, but symmetric key encryption is much faster. But public key encryption is very useful for authentication, for signing things, a digital signature. When we only need to encrypt a small amount, the time doesn't matter so much, and therefore we can provide a signature. We'll come to a digital signature on the later slides. There are different algorithms. Same with symmetric key encryption. We mentioned some of them. We mentioned AES, DES, triple DES, and a list of others on one slide. For public key encryption, there are different algorithms. A very popular one of the most prominent ones was RSA, and still used. RSA is a public key encryption algorithm. But there's some others, and they all depend upon solving mathematical problems. The security of them depends upon the difficulty in solving some mathematical problems, like factoring primes, solving logarithms, and so on. And we're not going to go into those algorithms, but they have completely different designs than the symmetric key encryption algorithms, so that we can use one key to encrypt and another key to decrypt. So there are different algorithms. RSA is a common one. We will see in some, you'll see later in some topics mention of things like Diffie-Hellman, maybe elliptic curve cryptography. Primarily used for digital signatures, which we'll cover shortly, and also key exchange, which I'll also show an example of. The design of the algorithms, the requirements of the algorithms, we're not going to cover. There's a few slides on the details, which we're going to skip over on public key cryptography. RSA, the details of that we'll definitely not cover. So RSA is one popular algorithm. It's not so hard to understand, but we will not cover it in this course. We will see examples of use using software. So regarding performance, public key cryptography algorithms are generally much slower than symmetric key cryptography. So therefore, when we have a large amount of data or time is very important, we would encrypt using symmetric key algorithms. So what role do public key cryptography play? They're very useful for sending secret keys. Let's show an example of that before we summarize the assumptions. Let's say we have our two users. We have, come back to user A and user B. A has a lot of data to send to B. And because encrypting with symmetric key cryptography is much faster than public key, we'd like to encrypt this data, gigabytes of data, using a symmetric key algorithm. And an example of symmetric key algorithm, just list one of the names. A very common one, or popular one, is AES, the Advanced Encryption Standard. So that's a specific implementation of symmetric key cryptography. So to encrypt the data, we need to have a key known by both A and B. Let's say A chooses a secret key, KAB. How does B know KAB? A chose KAB, chose a random number, 256 bits long. How does B know KAB? How does B know those 256 bits? In practice, how do we get this key from A to B? Send it to them. If we send the key to B unencrypted, and someone intercepts that, then they can learn the key. So we can't send the key to B unencrypted. B needs the key, A chose one, they haven't met each other before, they're on the other side of the world. They need to send it across a network. They can't send it unencrypted, because if someone intercepts, they'll learn the secret. So they must encrypt this key. How can they encrypt this key such that they can send it to B? They could encrypt using another symmetric key encryption algorithm, but they'll need another key to encrypt with. So what we do is we encrypt the secret key using public key encryption. Let's see how it's applied. So we have another algorithm that we're going to use, a public key algorithm. And the example of the popular one is RSA. And with that, every user has the key pair. A knows PUA, PRA. A knows its own key pair. They generate their own key pair, the public key and private key of A. B has a key pair, PUB, PRB. And what else does A know? We'll assume that A knows PUB. How does A know PUB? It's public. Maybe they posted it on a web page, or they sent it in their email in the signature every time they send an email. So because it's a public key, it's not so hard to distribute. So the public key of B we'll assume is also known by A. Well, there are some challenges in distributing the public key. Someone could try and create a fake public key of B. We'll not cover that yet. We'll assume that A knows the real public key of B, but it's not a fake one. We'll see maybe towards the end of the course when we look at web security and digital certificates, some of the ways to overcome getting fake public keys. But when we say a key is public, we assume anyone can know that value. Similar, B knows the public key of A. So that's what's known up front. We need to get key KAB to B. So what we can do is encrypt it. Create some ciphertext, encrypt using the algorithm, I'll just write the name here, RSA, the public key algorithm, encrypt KAB using a public key algorithm to send confidentially to B. What key will we use to encrypt it? To send to B so that no one else can see it. Which key should we use here? You've got 4 to choose from. A has 4 keys there. Which one is it going to use to encrypt? What do you think? Public key cryptography. For confidentiality, which key do we encrypt with? We encrypt with the public key of the destination, PUB. Using the public key of B, we encrypt KAB, the secret value that we chose. We send it. As we send a ciphertext to B, and B tries to decrypt. Decrypt the ciphertext C1. What do they try to use as the key? If they think it came from A, what do they use as the key here? It was encrypted with PUB. They are B, they use PRB. They receive a message encrypted with public key encryption, they'll try to decrypt it with their private key. Who knows PRB? Only B. Therefore, only B can decrypt. And that successfully decrypts because the corresponding keys in the pair we use for encrypt and decrypt. So we get as an output the original plaintext. What was the plaintext? KAB. Now B knows KAB. An attacker, if they intercepted the ciphertext, would not be able to decrypt because they don't have PRB. So an attacker would not be able to learn the secret key. Now that B knows KAB, the data can be encrypted, I'll say C2, the second set of ciphertexts, using the symmetric key algorithm. That is sent, and we can decrypt, because we also know KAB. And when we decrypt the ciphertext using KAB, we should get the data as output. So here we're combining symmetric key encryption and public key encryption. And the reason is we're using public key encryption to send the secret key from A to B. That is to send KAB from A to B, so that no one else can see that secret. And we're using symmetric key encryption to encrypt the data. The reason we use symmetric key encryption to encrypt the data is because it's fast. It's faster than public key encryption. So when we have a large amount of data, this will be faster than using public key encryption for everything. So that's a very common way to combine the two techniques. That's key exchange or key distribution. Any questions on symmetric and public key encryption? To be precise, I should have, when I used the decrypt function, I should have wrote decrypt here with RSA and decrypt D subscript AES. Right? I encrypted the key using RSA as the algorithm, and I encrypted the data using AES as the algorithm, just as an example of the different algorithms available. Any questions before we move on to the hard part? We'll introduce some more complexity in a moment. So make sure we're clear on this, otherwise the next part won't make any sense. Okay? Alright, no questions. I hope most people have got there. So public key encryption in practice is commonly used for this purpose, key exchange. So the benefit here is that the key itself is usually quite small. About public key encryption are listed here as well as on the other handout. Similar to what we said along the way, that decrypting with the right key will produce the original plaintext and we'll be able to recognise that it's correct. Decrypting with the wrong key, a key from a different key pair, or not the opposing key in the correct key pair, will produce the wrong plaintext, not the original one, and a decryptor will recognise it's wrong. So these are similar assumptions we've made before. Let's look at the remaining topics. There are three topics here: key management, digital signatures, and random numbers. We're going to just focus on digital signatures. What is key management about? Key management is how to get keys from A to B. We just saw an example of key management. How do we get KAB from A to B? We encrypt it with public key cryptography. So that's one form of key management, but there are others. There comes issues of using different levels of keys, master keys, session keys, how long to use keys, and so on. We will not discuss key management in depth today. We will look at it when we come up with passwords a little bit, and maybe when we return to web security, securing access to websites. We'll go through digital signatures, random numbers. How do you generate a random